Hi folks, Mr. Ackerman here. Thanks for watching. We are starting a new unit, and the topic of this unit, as you can see, is called uniform circular motion. What we're going to be discussing in this video is some examples of uniform circular motion, and of course after we do that we'll be able to properly define uniform circular motion, which I also call u.c.m. for short, and then we'll talk about some basic equations and some examples. In order to save time in the videos from now on, I'm not going to go over the schedule and the learning goals and success criteria. I'm just going to let you pause the video right now to see where we're at in the homework schedule and also what you should be hoping to learn and be able to do by the end of today's video. So pause now and have a look at these, make sure you know where we are, and then resume the video. Okay, so I presume you've already done that and you're now back, so we're going to dive right into things. First of all, uniform circular motion, I think you're really going to enjoy this topic. There's a lot of examples of uniform circular motion in our lives, and there's kind of something for everyone. To give you some examples, take a look at this roller coaster track. By the way, all of these images are off of Google Images, just to give some credit over there. They're not mine. In a roller coaster, so now we're talking about amusement park physics, there are obviously circular paths. Now these are not exactly circles, they kind of look like teardrops, but to a rough approximation we will be talking about the physics of roller coasters as we talk about the loops that they go through, and of course there's other rides that go in circles as well. I know many of you are interested in engineering, so looking over here, I suppose this would be an example of civil engineering, designing roads, highways, and whatnot that have obviously curves. There are on-ramps and off-ramps. That is a huge branch of civil engineering, and if you're going to go into that line of work, then you have to understand the basics of circular motion. So there's an application for you guys. Here's a device called a centrifuge. It takes samples of fluids such as blood, and it puts them in a test tube and spins them around really, really fast. That's an example of circular motion. In doing so, it separates the cell components, and then a researcher in a laboratory can study them. So here's a biophysics example for you guys. And finally, one that I really enjoy, this is what I studied in university. Here we're talking, of course, about astronomy. If you come close to your screen, you can see this is a diagram of the orbits of the planets, including Pluto, which are going around the Sun. It also includes the asteroid belt, so some of what are called minor planets. And what you notice is that most of these are pretty circular paths. Pluto kind of has an elongated path, and we call that an ellipse. However, it is sort of circular-ish, and we will be able to talk about the paths of planets as they orbit the Sun. And in fact, even stars as they orbit a galaxy, and we will talk about some really interesting applications later in the unit. So there's something for everyone. Let's move on to the next slide and talk a little bit more about the physics. So what we're going to do when we're talking about uniform circular motion, or u.c.m. for short, is we're going to have to realize, first of all, that there is acceleration going on. And now let me get into some details here. So imagine that an object is moving in a circle, and of course we've been talking about the u in uniform, so I guess it's time to define what that means. The u in uniform means that the speed and the radius of the circle are constant. In other words, it's the simplest type of circular motion that you can be talking about. This is the uniform, as in uniform circular motion. So to define uniform, once again, it means the speed and radius of the circle are constant. What is the radius? Of course, it's from the center here out to the edge. This is what we mean when we talk about radius. So let me write that in. And I hope some of you are kind of scratching your head right now and saying, why is he talking about acceleration if he's now telling us that the speed of the object moving in a circle will be constant? If you thought that, or if that now makes sense to you, then good. It means you're thinking about what's going on here really carefully. And yeah, if you're going in a circle, how can you be accelerating? Well, keep in mind, while your speed may be constant, in other words, you're going at a steady rate around the circle, and your radius can be constant, keep in mind that your velocity is changing, even if you go in a circle at a constant velocity. Why is this the case? Well, think back to what you know from grade 11 and also a little bit of grade 12 about movement along a curved path. If you recall, the velocity vector of a moving object points tangent to its path. So, for example, if the object is right over here, moving in a circle, and let's imagine that this is the direction of motion in the circle, so we're kind of going, I guess you'd call this a counterclockwise circle. So let me just use a different color here, and let's see where the tangent of the path takes us. As you learned in math class, the tangent to a circle is of course perpendicular to the radius. So, whoops, can't do that, but I can do this. I can draw myself a little right angle. This would be an example of the instantaneous velocity vector at this point in the circular path. And of course, a short time later, the object will have moved. It'll be, let's say, over here now as it goes along in its path. And therefore, I'll have to draw a new velocity vector, which has to be, of course, tangent to the path. So that might be here. And I'm also going to show that it's perpendicular to the radius. This would be a v instantaneous. You notice I'm putting the vector hat, which means I'm talking about velocity now. This might be v instantaneous 1, and this might be v instantaneous 2. What do you notice? These vectors, while they are the same magnitude, which is telling us that their speed is constant, their directions are not the same. And that's what I'm getting at when I'm saying that there is acceleration here. There is an acceleration because the velocity vector's direction is changing. You can see it pointing in a different direction. Therefore, we've got acceleration. Plain and simple. So now you know why the topic of this slide is called acceleration. Whoops, not drawing very straight lines there. The topic, of course, is called acceleration. However, you might be wondering, what the heck is this word, centripetal? You may never have heard this word before. Well, you have heard part of this word, center. That's where this comes from. However, what does centripetal mean? Well, we're going to learn that in a second. In your textbook, and this textbook, by the way, is Physics 12 by Nelson, there is in section 3.1, figure 4, a diagram similar to what I just drew for you. It shows an object moving in a counterclockwise circle once again, and it shows you at position 1, radius 1, the object is located right here, and of course its velocity vector v1, tangent to the path, points this way. The object moves in a circle, and a short time later it's in position number 2, designated by radius r2, and now it's got a new velocity vector pointing in a different direction. They call that v2. They show you the angle theta through which the object has rotated, a certain fraction of the circle. And if you read carefully in this section, of course, they're talking about uniform circular motion, so they want you to assume that the speed, and therefore the magnitude of this vector, is constant. Okay? Now what they do next is they show you radius vector r1, which of course is pointing this way. That's right over here. This matches up with r1 over here. And here's radius vector r2, which matches up with radius vector r2 over here. And they want to show you that the radius vector has changed. The symbol for change in math, of course, is the Greek letter delta. So they draw in the delta in the radius vector. Now, how do they do this? Well, it's kind of simple, really. If you take a look at it, you'll see here's radius vector number 1. It changes, and if you follow the change, you get yourself to radius vector r2. And so they call this vector delta r. Okay? r1 plus a change in r, delta r, gives you r2, the final. That's a very basic idea. An initial amount of something plus a change gives you a final amount of something. And this, of course, forms a triangle. Now, let's take a look at another diagram here, this one dealing with the velocities. You notice back up here, v1 is pointing this way, while v1 over here is shown down here. v2 is pointing that way, and there's v2 shown here. Okay? And the same idea applies. an initial velocity plus a change in velocity, called delta v, is your final velocity. An initial amount of something plus a change gives you the final amount. So what have they done? They've shown you that v1 in this diagram up here is actually pointing inward. Sorry, that's delta v1, or sorry, delta v, tripping over my words here. Delta v points this way to the left. And what do you notice about the change in velocity? Well, it's actually pointing inward toward the center of the circle. And now you know why the acceleration is called centripetal, because it points inward toward the center. In fact, the word centripetal means center seeking. So there you go. Centripetal acceleration is what we're dealing with when we have uniform circular motion. The speed isn't changing, the radius isn't changing, but the direction of the velocity is changing, therefore there's acceleration. What direction does it point? Taking a look at this diagram, which I'm sure you'll have to look at and think about after you watch this video, the change in velocity vector points inward, and that means we have an acceleration toward the center. Now, let's talk a little bit more about this. AAV, which is our formula for average acceleration, is of course delta v over delta t. It always was and it still is. So now you see why the delta v vector is so important when we're talking about acceleration. It's because it's pointing inward toward the center. That's telling us that this acceleration is inward toward the center. However, when we want to solve for an actual formula for the average acceleration here, we need to know how much time is involved. Well, here's where we get into a little bit of tricky calculus. And I'm not going to go into this in great detail with you because calculus is not a prerequisite for this course. However, for those of you who are taking calculus or who have already taken calculus, what I want you to do now is go back to the book, Figure 4, and look around that page where you're going to see them use this diagram, this series of diagrams here. They're going to talk about these triangles here, and they're going to use a physics idea called a limit. And with that idea, which of course makes sense to all of the physics students or the calculus students in the class, but maybe not if you haven't taken calculus, that idea is going to lead to a formula for the centripetal, center-seeking acceleration. You can learn this formula out of the textbook if you want. I'm not going to ask you to derive it because, again, it requires calculus, which is not a prerequisite. So let's jump now to what the actual formula is and then talk about an application. So if you're reading along in the book, or if you just want to watch on the video here, the formula for average acceleration, and this is for the magnitude only, so I put the absolute value symbols, is this. The book gets down to this formula: speed squared divided by radius. It's a very simple formula. If you check the units here, you'll have meters per second being squared on in the numerator. You'll have meters in the denominator. And what's that going to give you? It's going to leave you with meters per second squared, which are in fact units of acceleration. This formula is telling you that the acceleration that an object going in a circle experiences depends on two things. First of all, how fast it's going. Speed is in the numerator, so more speed equals more acceleration. Of course, the radius comes in the denominator. That means less radius also equals more acceleration. Now, does this make any sense? Well, to give you an idea that it does actually make sense, I want you to consider a sport that a lot of you love and a lot of Canadians love. It's called hockey. And I want you to imagine that you're skating in a circle. Here's two circles. I'd like you to imagine that in one circle, the radius is very small, but in another circle, the radius is much bigger. And I want you to think, if you've ever gone skating, which circle is easier to make at any given speed? Are small circles easier to make at a given speed, or are large circles easier to make? For that matter, you don't even have to have ever skated in your life. Have you ever just run around in a circle? Or have you tried to ride your bike in a circle? Have you driven a car in a circle? What kind of circle is harder to make? one where you're going at a certain speed and you have a small radius, or a large radius. I think you all know that this one is harder, this one over here. In other words, your velocity is changing much more rapidly, therefore you have a greater acceleration. Yeah, smaller radius at a given speed does equal more acceleration. And now let's look at the other side of this formula. How does the speed affect the acceleration? Well, for any two circles of a given radius, what I want you to think of now is which one is harder to go in a circle, go around. Well, if the radius is constant for both of them, I think it's pretty clear that the faster you go, so let's imagine that this is a slowly progressing circle, and this is a faster one. The faster one, it's much harder to go around in a circle because your acceleration is so much greater. This one would be harder. So the higher speed leading to higher acceleration also should make sense to you. In other words, this formula, which I'm not telling you exactly where it came from because it requires calculus, but if you read the book you can find out, it makes sense from a dimensional standpoint with the units, and also from an intuitive standpoint of just analyzing what does it feel like to go in a circle. Something else for you to consider. Let's take a look at this diagram right over here for a second. If you're moving in a circle, then that means every time you go around, you cover a distance equal to the circumference, that's 2 pi r. And if we're talking about circular motion, it means that you are repeating your motion over and over again. In other words, it's periodic motion. Do you remember from grade 11, the time to go through one repeating cycle is capital T, called the period. So in uniform circular motion, your speed, which of course is distance over time, is going to be 2 pi r over t, the period. So what I want you to try to do right now is to take this and sub it in to the formula for the acceleration when you're moving in a circle at a steady speed and a steady radius. If you work this out correctly and square everything properly, you're going to come up with a new formula which looks like this. The magnitude of the average acceleration, it's going to be 4 pi squared r over t squared. This is a second formula for centripetal acceleration. And finally, thinking back to grade 11, if you recall, period is just the reciprocal of frequency, f being frequency. So now I want you to sub this into your new formula over here and satisfy yourself that when you do this, you get 4 pi squared r f squared. In other words, the t squared in the denominator becomes an f squared in the numerator. So in the end, and now I'm going to go to another slide where we're going to do an example. In the end, you have three formulas for the acceleration. They are v squared over r, if you know the speed in meters per second and the radius. Or it could be 4 pi squared r over t squared, if you know the radius and the period of rotation. Or it could be 4 pi squared r f squared, if you know the radius and the frequency of rotation. Of course, we don't have to keep calling this AAV, average acceleration. Let's call it what it really is, because it's a special kind of acceleration. It's centripetal, so the symbol becomes AC, the C standing for centripetal. And I'm going to leave you with one example, and the example is this. Getting back to the astronomy, what I'd like you to do is to calculate, so I'll type this out, calculate Earth's centripetal acceleration as it orbits the Sun. And I'll just put that down here so you can see it a little more clearly. The Earth, of course, is moving in a nearly circular path around the Sun. What is its acceleration? Well, let's see. If we want to know that, we need to use one of these formulas. All of them have the letter r in them, so you are going to have to know the radius of Earth's circular path. Some of you may know this because maybe you like astronomy and you've read it somewhere. Others will have to look it up. Go ahead and look that up right now. Pause the video, go on Google, and find out the radius of Earth's orbit. So, first thing, radius of the orbit. Pause the video, come back when you've got it. Okay, you're back, and hopefully you have figured out a handy way to remember this. 150 million kilometers, which of course, since we want meters, will be 150, and then we've got a million there, that's times 10 to the 6. And then kilometers, we've got to get into meters, so times 10 to the 3. What's that going to give us in meters? This one is 1.5 times 10 to the 2. So 1.5 by 10 to the 2, the 6, and the 3, that's going to give you 11. So we've got 1.5 times 10 to the 11 meter radius. That's a large radius. It's getting up close to 1 trillion meters. Okay, now what else do we know? We also need to find out either the speed of Earth going around the sun, which some of you may know. Maybe I think I've mentioned it in class. Maybe you remember it, or maybe you've learned it. We could also know the period of Earth's orbit, or we could know the frequency of Earth's orbit. Feel free to look up any one of these. This one's a neat one to look up, and I'll ask you to do that now. Okay, you're back, and if you've looked this up, it's around 30 kilometers per second. However, I wouldn't expect everyone to know this off the top of their head. How about this one, the period of Earth's orbit? Do you know the period of Earth's orbit? The answer is yes, you do. As a member of this planet, you should know that Earth orbits the sun once per year. Okay, if you feel kind of silly because you didn't know that, then don't feel too bad. All of us sometimes get tripped up over seemingly difficult things which are actually quite simple. But yeah, Earth does orbit the sun in 1 year. But you got to get that into seconds. So here we go. T equals 365 days, which equals 365 times 24 hours. Let's put this is days, hours per day, times 60 minutes in an hour, times 60 seconds in a minute. And what's that going to give you? I've got my calculator here, you've got yours there. If I remember this one correctly, it's around 31 million. I've done this a few times. 365 times 24 times 60 times 60. And I get 31 million. I'm just going to go to one more sig fig there, times 10 to the 7 seconds. And so now what I'd like you to do is take these numbers and right up here, let's compute the centripetal acceleration of Earth. And I guess we're going to use this formula here because this is the one where we know most of the info. So what are we going to get? The centripetal acceleration, 4 pi squared times 1.5 times 10 to the 11 meters over 3.1. By the way, down there, that should be in there. 3.154 times 10 to the 7 seconds. And don't forget to square that, folks. And what do you get? So let me just type this in. I'm going to store that number in the memory. Okay, here we go. 4 times pi squared equals times 1.5 times 10 to the 11. And I've got a number there. I hope you guys are working along with me because I'm trying to do this on my phone. Not easy, but at least I don't have to carry a calculator around with me. And that's divided by 3.154 by 10 to the 7. Did I get that? No. I gotta tell you, typing this in on a calculator or on a phone is really annoying. 4 times. I'm just gonna pause this video while I do this. Okay, folks, I'm back. I have mastered my calculator, or conquered it rather. What did you get? I finally typed this in, and here's what I got. To 1 sig fig. I got 6/1000ths of a meter per second squared, and without checking, so I'm going to check that one more time. I always thought it was 6/100ths. Here I go, I'm pausing one more. And hey guys, I'm back. Yeah, as it turns out, that is correct. I did something right for a change. 6/1000ths of a meter per second squared. That's not a lot. Do you know any other acceleration to which you might compare this number? Of course you do. As a physics student from grade 11, the first thing that comes to mind when we talk about acceleration and familiar numbers, maybe it's acceleration due to gravity on Earth. What's the value there? It's 9.8 meters per second squared. This is only 6/1000ths of a meter per second squared. So the acceleration of Earth in its orbit around the Sun is absolutely negligible. It is not even worth talking about when we talk about acceleration due to gravity, due to the Earth's own gravity. And now you know why, when we talk about an idea that actually predates this video, remember accelerated frames of reference? And we were talking about how the Earth is often considered an inertial frame of reference, a non-accelerated frame of reference. Well, you know that's not true. Earth is going in a circle orbiting the Sun. However, now you can calculate that value. It's so much less than the acceleration that we experience on a daily basis when we talk about free-falling objects that it can be safely ignored. It's a tiny, tiny number indeed. All right, and by the way, I'm going to start something new in the videos. There's always going to be a fact of the day or a fact of the video, something interesting, and I'm going to start asking you questions in class when you come in each day to make sure that you've been watching the videos. And this will be a quick way to rack up some easy marks. Yes, it'll count for marks. And I'm also going to attach a little prize to it, so whoever has the most marks at the end can win a little prize, maybe at the end of the unit or the end of the semester. So this is to encourage everyone, of course, to watch the whole video. So today's fact is this calculation, the calculation of Earth's acceleration as it orbits the Sun. So you'll probably want to remember 150 million kilometers as our orbital radius. You'll probably want to remember how to figure out the period, and then you'll want to remember how to calculate the acceleration and remember this number so you know whether you got it right. Okay, folks, that's it. I will see you in class. Have a good day.